Hi guys, today we're talking about the diffraction of X-rays and particles by crystals. So the problem here says a wavelength of 0.129 nanometers characterizes K-alpha X-rays from zinc. When a beam of these X-rays is incident on the surface of a crystal whose structure is similar to sodium chloride, a first order maximum is observed at 8.15 degrees. Calculate the interplanar spacing based on this information. So we've got our crystalline structure here, and this is sodium chloride, and we've got our, these are ions, so we've got our sodium ions and our chlorine ions. And what happens is these X-rays are going to hit with these ions and they're going to reflect off, okay? And so theta is going to be, so you've got the distance, this is the interplanar distance between these ions, and so theta is going to be basically the angle from the interplanar spacing right here and the reflected beam. Okay, so anyways, and of course this is also theta if you were to take the interplanar spacing right here and then we were to draw a line through here which would actually hit it should actually go to right here. Okay, that would be theta. Right. So anyways, so the equation we're going to be using is 2d sine theta is equal to m, and that's just going to be our maximum, okay, or the first order maximum. So since we're using first, our m is going to be 1. If it was 2, you'd use 2, 3, so on and so forth. All right. Times the wavelength. So we've got to find d. So all you have to do is take our first order maximum, which is 1, and we're going to multiply it by 0.129 nanometers. Right? And then we're going to divide it by sine theta, and theta is 8.15. Right? And when we do that, so we took the first order maximum, which is 1, times the wavelength, 0.129 nanometers, and then times 2 times sine theta, and we get, so that's to the negative 10th, so you throw it over, 0.45 nanometers. So 0.455 nanometers. Alright, so that is this, which is from here to here, and that is D. Okay, so that's pretty simple. Now let's say that we did not have theta, but we had D, the interplanar spacing. So let's say that. How would you rearrange this? Well, so now we have D, but we don't have theta. So basically, you're just going to rearrange it so that it looks like this. Theta equals m, well, okay, yeah, m, which is our first order maximum, times the wavelength, 0.129 nanometers, divided by our 2d, so let's say, so the distance was that, so we take 2 times 0.455 nanometers, right? And then you're going to throw the sign over, but when you do that, it's going to become the inverse. So all you have to do is do that, the inverse of sine, which is sine negative 1. And when we do that, sine negative 1 times 1 times our wavelength divided by 2 times the distance is going to give us theta, 8.15, which is what we had. Alright, so do that. Theta equals 8.15. I was just showing you they asked for something else. Alright, and then down here I just drew like a little picture of what's going on. You've got your X-rays. It's going through this little slit, and then it's going to go through this crystal, which is this. So the crystal is that whole structure, and then what's going to happen is it's going to be uh, you're going to have these x-rays that bounce off, and then they're going to be shot out here in like a pattern, okay? And if you were to look at this pattern, thinking this is basically what it would look like, okay? And that is photographic film. Anyways, easy problem.